We are starting 9.9, which is next section in our syllabus. 9.9, and we will do this section 9.9 from both books. Actually, this section, let me rename this. This section is 9.9 dash 4.8. 9.9 from ZIL book and 4.8 from the second book, Elements of Electromagnetics. Elements of electro. In the syllabus, it is written electrodynamics, but it is not a correct word. It is electromagnetics. And title of this section is Independence of Path. Independence of a path. This is the title of this section. Yani when we integrate a function over a curve, path mean, of course, it is some curve path, then the integral does not depend on the, suppose we have a point A, it can be in 2 dimension or in 3 dimension. We have a point B. So if we have a path from A to B going like this, and we integrate a function, a vector field dl, f dot dl. Let me write this in Cartesian coordinates, and same concept is in the other coordinate systems. So let us say, let this vector field f as a function of xy or xyz is p of xyz I, but this time here with the notation of the new book, we can say ax and this unit vector plus, or let me write on this, maybe I will change this one. So first let me write, let f as a function of xyz is a p of xyz ax plus q of xyz ay plus r of xyz az, where ax, ay, az all are unit vectors. So they are I, j, k. And dl and the path can be given in different ways from point A to point B. If it is in 2D, it can be given by parametric equations or Cartesian equation. If it is in 3D, then the only choice we have that this is given by parametric equations. Then there is no one Cartesian equation which describe this curve. So the curve C, let's say the curve name is C or L, whatever you call it. So let us call it as L. So this L vector field F is given here, and L is as consists of x equal to x of t, y equal to y of t, z equal to z of t, where t is between two real numbers a and b. When t is equal to a, we get starting point capital A. When t is equal to b, we get the ending point capital B. And what is dl, this vector? It is dx ax plus dy ay plus dz az. This is dl. You know this from previous chapter. And integral over L f dot dl. It can be written as integral from a to b p of x y z dx plus q of x y z dy plus r of any their dot product x y z dz. Okay. Now our concern is independence of path. Yani, do we get what is the situation under which if we choose some other path, like for example this red color path, or if we choose some other path like this blue color path, or maybe some other curves like for example this one, for example this path. So question is, what is the condition that we get the final answer independent of path? It depends only on the endpoint. Now this concept, this idea is similar to, if you remember from your calculus, that a definite integral from a to b f of x dx is equal to f of b minus f of a, where what is the capital F? That is antiderivative of small f. So antiderivative of small f of x dx is capital F of x, or you say derivative of capital F of x should be small f of x. So this integral depends only at the endpoint a and b. The same concept we are going to explore here, that what is the condition under which we have this independence of a path. We have this independence of a path. So here is the theorem, or not theorem. First is just a definition. Definition of first definition here is for conservative field. Conservative field. First, we need to learn this one. To learn more about these things, independent of path. So first definition, so under what condition? Let me write the integral is independent of path. It depends on endpoint only. Okay, for this, first we need to learn a definition. What is this definition? That a vector field or vector function in 2D or 3D is said to be conservative if it can be written as gradient of a scalar function phi. If it can be written as gradient of a scalar function phi. Now, you guys are electrical engineering students? Kebab?
Yes.
Yes. So for you, we say that an electric field an electric field E is said to be conservative if E can be written as, if let me say, if there exists a scalar function or field V such that this vector field E is equal to negative of del V, yani gradient of V. Del V mean gradient of V. Del V mean gradient of V. And we know that gradient of a scalar function is a vector function, so we have this vector field, vector function E. Okay. So this is first thing, that when do we say a vector field is conservative? This definition is for a general field. In general, whatever vector field is, but in particular, when this vector field is in an electric field, then we say that this is conservative if there exists a scalar function phi. Now, this scalar function phi is called potential V is called potential of for E. V is called for E. V is called a potential function for E. Okay. So far we just learned definition of conservative field. Okay. What next? And you know what is the gradient? You know what is the gradient? How do we know that a vector field is conservative? And that is test for a vector field to be conservative. A test for vector field to be conservative. Okay, you can check in two ways. Number one, similar to what you learn in Math 202. Some of you, maybe all of you, I don't know, they may have taken this Math 202 course. And in Math 202 course, you learn one thing called similar to exact differential equations. What partial p over partial y is equal to partial q over partial x. Partial p by partial z is equal to partial r by partial x. And partial r pqr. So p by z, r by x. So partial q by partial z equal to partial r by partial y. So p with x, p with y, and q with x. First component with y, second with x, and p with z, r with x, q with z, r with y. So if these conditions are satisfied, or very easy to write del cross f, del cross this vector field f is equal to a zero vector. Del cross f is a 0. So one of these two you can use to check if a vector field is conservative. Okay. Now, when a vector field is conservative, then we say that the integral is independent of path. It is independent of path. And this is the next theorem. Let me just copy this theorem here. Uh, 992. Where is 991? Fundamental theorem. Fundamental theorem. And actually that fundamental theorem, it should be equivalent concept. So there are two equivalent concepts. Let me first give you this, and then I will tell you, okay, now let us see how to solve this one. Okay, now this is theorem 992. What in an open connected region R, integral over C f dot dr is independent of path C if and only if the vector field F is conservative. So here in our notation, with our notations, we say that the L F dot, we do not say dr, we say F dot dl. In this book, they are using C for curve and dr. In our say book, the other book, electromagnetics, we use L and dl. With our notation, it is F dot dl. Is independent of path, does not depend at the end points. Only depends only the end points, does not depend on the path. We go from point A to point B. If and only if this vector field is conservative. And an equivalent concept is that when the path is closed, when the curve is closed, so it depends on the end point. And when curve is closed, then the integral will be equal to 0. Okay, I think let me just go by the same tartib order what is given in your book for these theorems. Okay, so here is that theorem. First of all, we have this theorem. What this theorem says, 991. It says that suppose C is in an open region R in XY plane or XYZ plane, then we say that if F is conservative and phi is a potential function, then this integral is 0. Okay. Now, since we are using, this is from your book, chapter 9, ZIL book, main book, and theorem 991. And here, with our notations, or let me say simply, or this vector field over L, because we are using F and dl, and you know that when F is conservative, by definition, it is written as gradient function of a V. So instead of phi, we are using V dot dl, gradient V dot dl, and gradient V is a vector quantity. Gradient of a scalar function is a vector quantity, and that is equal to v at the end point minus v at the starting point. So in our notation, we have, instead of c, we have L, and instead of phi, we have v, and we are writing this for 3D. Okay. Now, the equivalent concept is that instead of, when integral does not depend on the path, we also say it is independent of path. When integral depends only at the endpoints, then it is independent of path. It depends on the endpoints only. So we also say that this integral is independent of path if and only if the vector field is conservative. And now, if we have a closed path, if the path is closed, yani, suppose we have like this one, then point A and point B are equal. So VB minus VA will be equal to 0. It means this integral is 0. If we have a closed path, then VB is equal to VA. So VB minus VA is equal to 0. So we can also say this one for a closed path, only for a closed path. So these are equivalent concepts. Now, here it also comes that how to find V. This is a question. How to find V? And that's how to find the, if F is conservative, fine, okay, it is conservative. But then the question is how to find the potential function phi. So the next thing is how to find the potential function v of xy in 2D and xyz in 3D. Before this, we just learn definition that when do we say that a vector field F is conservative? Then when it is conservative, then what happened with the integral? We can evaluate this integral. We can evaluate this integral using the potential function V. Okay. And if F is conservative, we also say that integral is independent of path. If curve is closed, then the integral will be 0. Okay, fine. But so far we did not say anything about how to find the potential function phi. So, you know what F we are writing here, we are using here, F is equal to, I am skipping x, y, z. So P AX plus Q AY plus R AZ. And this V is a function of x, y, z. So F is conservative, mean F can be written as gradient of V. F yani P AX plus Q AY plus R AZ is written as gradient of V, and you know that gradient of V mean partial v by partial x ax plus partial v by partial y ay plus partial v by partial z az. If this is true, then we say it is conservative. So what does this implies? It says that P or P of x, y, z is equal to partial v by partial x. Q is partial v by partial y, and R is equal to partial v by partial z. And what do? We integrate this, take any of them. So take any of them and integrate. These and integrate. This is step 1. So I take first one and integrate, and as a result I get what? V of x, y, z equal to integral P of x, y, z dx, we integrate with respect to x, plus constant of integration. Plus constant of integration is a function of y and z. Y and z. Because when we take derivative on both sides, we will get partial v by partial x equal to p, derivative antiderivative cancel, plus 0. Derivative of this part with respect to x is 0. Then second step is you take partial v by partial y take or differentiate with respect to masalan y, with respect to y, and put and equate with q, or put equal to q. Okay, when you take derivative with respect to y, you get partial v by partial y, and that is partial by partial y of this p of x, y, z dx plus partial f by partial y, and this is partial v by partial y, and we put this equal to q. When we put this equal to q to find f of y, z, then so to find f of y, z, and this f of y, z will be a function of y plus a function of some function of x. We will see this in example in more detail. So when we do this, we will get v of xyz equal to this integral plus a function of y and a function of x. And then again differentiate the answer in step 2 in the previous step. So maybe I write 1, 2, and 3. 1, 2, 3. Not 3 here. 3. Differentiate the answer we get in part 2 with the answer or the expression in part 2 with respect to z and put equal to r. Okay, to find this remaining function. So this will be equal to sum g of y plus h of x to find h of x equal to r to find h of x. So this is the procedure, and that procedure I will make it very, very clear by some example. Let us first do this example, and then we will do the other things. Okay, example. So let us take E, a vector field, as e power 2z ax plus 3y square ay plus 2x e power 2z az. So this is a vector field. Show that okay, the line integral between 2 points, show that the line integral yani E dot dl, show that the line integral between 2 points a 1 1 log 3 and b is, let's say, 2 2 log 3 in a simply connected region uh, line integral between 2 points, the line integral, show that the line integral between 2 points a and b in a simply connected region containing the path L from A to B is independent of path. That is integral E dot dl over L is equal to is independent of path. That is, this integral is independent of path. Okay. Show that. If so, if this integral is independent of path, find the potential function V such that this vector field E is equal to gradient of V and the integral over L E dot dl is equal to V at B minus V at A. So this is what we have to do. Okay, solution. So first thing is to show this is independent of path. And that I mentioned you need to show that del cross E is equal to 0 vector. So del cross E is equal to, this is a x, this is a y, here is a z, partial over partial x, partial over partial y, partial over partial z, the del operator. Then E from this question is e power 2z, 3y square and 2x e power 2z. So this is what we have, del cross E. Now this is equal to ax bracket partial derivative of 2x e power 2z with respect to y is 0. Similarly, partial derivative partial over partial z of 3y square is also 0. So ax with 0 minus ay partial derivative minus ay and then derivative is 2e power 2z and minus 2e power 2z, which will be 0 by cancellation, plus az derivative partial over partial x of 3y square is 0, partial y of e power 2z is also 0, so this is 0. So we say that this is equal to 0 vector. So we say that So vector E is conservative and the integral is independent of path. Okay, so one part we have done. Part B, to find the potential function phi. Now, find the potential. Okay, Shubham, no one is asking me anything. Tell me if something is not clear. Let me see if anyone is in the class. Shabab,
It's clear, Doctor.
Yes, Doctor.
find the potential.
We're here, Doctor.
Find the potential function V such that partial V by partial X is equal to P, and in our this vector field P is e power 2z, and partial V by partial Y is equal to Q, which is 3y square, and partial V by partial Z is equal to R, which is 2x e power 2z. Now, I will do those three steps which I show you. So take first, integrate with respect to x. So you get v of x, y, z equal to integral of e power 2z will be x e power 2z, 2z as a constant. So integral is x plus a function of y and z. Now, then take or differentiate with respect to y. So first part is 0, no y. Second part, partial f by partial y. And we put partial f by partial y equal to q, which is 3y square. And this implies f of yz, yani we integrate this with respect to z. With respect to y. We take this one, integrate with respect to y. So f of yz is actually y cube plus constant of integration. So let me write that constant of integration will be either constant or a function of z. So we have a function of y, pure y, and then z, and with this our v of x, y, z become x e power 2z plus y cube and some function g of z. What did I call it here? Sorry, it should be h of z. So here I'm calling it h of z. So let us keep the same notation, h of z. So now the third step, whatever we obtain in this step, we take partial derivative of this, differentiate with respect to z, and when we differentiate with respect to z, we get 2x e power 2z plus y cube is 0 and plus derivative of h with respect to z. And we put this equal to r. R is 2x e power 2z. So this implies that h prime of z is 0. So h of z is a constant. H of z is some number, some constant. And we take this constant equal to 0. Take c equal to 0. You can take c non-zero, but that gives you no benefit, no faida, nothing. Because when we apply upper limit minus lower limit, this c will cancel out. So if you want to keep it c, you can keep as a c, but this will not be any benefit. All right, whatever is. Now we are writing v one more time. X, y, z is equal to x e power 2z plus y cube plus c. We got it. So the integral e dot dl over L is integral from A to B. L is from A to B, independent of path. E dot dl, and by the theorem it is V at endpoint B minus V at A, yani V at 2 to log 3, 2 to log 3 minus V at 1 log 3. Let us do this calculation. Put in V, x equal to 2, y equal to 2, z equal to log 3. X is 2 and e power 2 log 3. What will be e power? Someone tell me e power 2 log 3.
9.
Tell me. Yes, Shabab?
9.
9. Very good. Plus y cube 8. Plus c minus, put 1. So x is 1 and z is 1. So it will be 1 multiply e power 2 log 3. Again it is 9 and y is 1. So plus 1 plus c, but we need to put a bracket here. Okay. So what we have here now, 9 to 18, 18 plus 8, 26 plus c minus 9 plus 1, 9, 1 multiply 9. So this is big dot, mean multiply 9 plus 1, 10 minus a c. So here you see this c will be cancelled. So this is why I said over there that you can take this c equal to 0. So 26 minus 10 is a 16. So this 16 is the final answer. Okay. Now, Shabab, there is one thing which is here for the electric potential. For the electric potential, we say that the E is equal to negative of gradient V. And in general, we say that the vector field is equal to gradient of a scalar function. But for when this E is electric field, when this E is electric field, then we say it with the negative sign. So let me put here note. If the vector field E is an electric field, then we write, and this electric field is conservative if this is equal to negative of gradient of V. We put a negative sign with it if it is electric field. So if our field, because here in the question, it is not saying that what this E is. We are not saying anywhere it is electric field. So if question says, show that the electric field is conservative, you need to put a negative sign. Show that the electric field is conservative, you need to put the negative sign. Put a negative sign with it. Am I clear? And you are electrical engineer, so you know much more better than me. Okay. Work done. So far here we are in chapter 9. And let me ask you this thing, Shabab. Work done by a force, work done in moving a charge Q microcoulomb from A, yani from point A to point B. This is equal to W is equal to Q time integral over L from A to B E dot dl. And this is, if this is Q equal to 1, then simply E dot dl. So I'm stopping here. I will continue from this point tomorrow, inshallah. And if you have any question, I'm here to answer. So today we did this one complete example, and so many these definitions and theorems and ideas. You make all these things clear, and we will continue from here tomorrow, inshallah, and do more problems.
Doctor,
Yes.
I have a question about the homework. I send you my solution, and
Homework.
you said it's wrong, but I wrote in the email it's the same answer. I said it's correct.
Who is talking?
That's Abdul Daj.
You mean homework or quiz?
No, quiz.
Quiz. The correct
Yes.
answer is 8.
Yes, I wrote in the email my answer is 8 with the picture of my solution.
No, in the picture it is not 8.
No, doctor, in the picture it's 3 plus 3 plus 2, which is 8.
Okay. Did I reply you?
Yes, you said it's wrong, but the correct answer is 8. And I
Okay, talk to me after 11:30.
Okay.
I don't want to talk this in front of other students.
Okay.
You may feel embarrassed, so talk to me after 11:30. Mazboot?
Okay, thank you.
Okay. Any other has any question, Shabab?
yeah, yes, doctor. The book